Okay, so in this video, we're going to take a look at powers of tangent and secant. All right, so before we jump into that, just a quick review of some of the stuff that we already know and an introduction to some new integrals here. So basic integral of secant squared tangent of x, right? That comes from the derivative of tangent being secant squared of x. And then the integral of secant x tangent x being secant of x, also coming from the derivative of secant x being secant x tangent x. Right? The integral of tangent x being the natural log of secant of x. This was in one of our last week's in class word problem set. Right? We did that. Right? Comes from a basic substitution. The integral of secant x is not a straightforward substitution. Right? It involves it's a bit more of a kind of nuanced way that they find the natural log. But for here, we'll just take it as fact that this is the integral of the secant of x. And our trig identity, right, secant squared x equals to 1 plus tangent squared x. It is derived from the Pythagorean identity, cosine squared x plus sine squared of x, where we divide through by cosine squared of x and simplify. So we're going to lean on these to help us integrate something like this, right? Tangent of to the 6th power of x times secant to the 4th power of x dx. Okay? So the approach I'm going to take here is I'm going to use this Pythagorean identity, right? I'm going to split the secant squared, or the secant to the 4th, into secant squared x times secant squared x dx. Right? And the reason being is, well, here I know the derivative of the tangent. Derivative of the tangent is secant squared x. Right? So I want to use that fact here. The only thing now left, if I'm going to use that as, it's for the substitution, well, I need everything else to be in terms of tangent. Well, I can do that if I have an even power, right? If I have an even power, I can use this identity. So going even further here, we have tangent to the 6th of x. You get 1 plus tangent squared of x. All right, and then again, I'll keep that secant squared x here. Right, I'm going to use that for my substitution in a minute. And then I'll distribute the tangent to the 6th power. Tangent to the 6th power x plus tangent to the 8th power of x times secant squared x dx. All right, and now I'm ready to do a substitution. All right, I'm going to let u equal to tangent of x. Right. Now, why just tangent? Well, because the derivative of that is right out here, secant squared x dx. All right, and now I can substitute. We get u to the 6th plus u to the 8th, right? A basic power rule integral. All right, and now doing that, we get u to the 7 over 7 plus u to the 8 over 8. Sorry, that looked odd here. Sorry. U to the 9th over 9. And again, don't forget the plus c. And then we're done, right? Once we're there, right, we did the hardest part was getting the substitutions, right? Then just back substitute. So we get tangent to the 7th of x over 7 plus tangent to the 9th of x over 9. And of course, plus c. Okay. All right. So here, we're going to get tangent. Let's do another example here. So another example, tangent to the 5th of x, secant to the 7th power of x dx. Now the approach that I did before is not going to work here, because if I break off a secant squared, right, there's no way to change those secant to the 5th that'll be left into tangent, right? That odd power doesn't allow me to do that, right? So instead, what I'm going to do is, if I can't kind of lean on this here, right? The derivative of tangent being secant squared, I'm going to lean on the derivative of secant being secant x tangent x. So what I'm going to do here is, instead of breaking off a secant squared, I'm going to break off a factor each of the tangent and the secant. Secant x tangent x dx. All right, and now work on changing in everything else, not in terms of tangents, but in terms of secants, to be able to apply a substitution. So here I'll rewrite this again as secant squared x squared, secant to the tangent squared. Okay, tangent squared x, secant to the 6th of x, and then our secant x tangent x dx. Okay, excuse me. All right, and now I'm going to use the identity here, tangent squared of x. So tangent squared of x is going to be equal to secant squared x minus 1 squared, secant to the 6th of x, and then of course our secant x tangent x dx. All right, and now distributing here, expanding, we'll get secant to the 4th power of x minus 2 secant squared x plus 1 times secant to the 6th of x times secant x tangent x. All right, distributing in that secant to the 6th, we get secant to the 10th power of x minus 2 secant to the 8th power of x plus secant to the 6th power of x. And again, here are secant x tangent x dx. All right, again, just saving it for my substitution, right? Since it is the derivative of the secant. All right, and now we're ready for my sub, right? My substitution is u equals to secant of x, just secant of x, right? And then du is secant x tangent x dx, right? Which is right here, right? Which is what we wanted, right? That's why we did everything in this particular manner. All right. And then from here, we get u to the 10th minus 2u to the 8th plus u to the 6th du, right? We get a nice expression that relies only on the power rule. All right, and now applying the power rule, we get u to the 11th over 11 minus 2u to the 9th over 9 and plus u to the 7 over 7. And of course, as always, the plus c, right? And then we won't forget here to back sub, so we get secant to the 11th power of x over 11 is 2 secant to the 9th power of x over 9. And lastly, secant to the 7th power of x over 7 plus c. Right? And that's how we approach this problem here. All right, now one more example here where sometimes we'll be left with, well, how do I do, for example, something like this, tangent cubed of x dx. Okay, now for here, we see we just have tangent, so there's no really secant to play around with. So the techniques that I used in the previous two problems do not directly lead us to necessarily a power integral, right? So what I am going to do is I'm going to split off a tangent squared, right? So I'll have tangent of x, and then I'll write times tangent squared x dx. Okay. All right. And then from here, right, I'm going to rewrite tangent in terms of secant. Right, so we get tangent x is going to be secant squared x minus 1 dx. Right, and as I distribute here, tangent x secant squared x minus tangent of x dx. Okay, now notice here we're not going to get one simple substitution that's going to solve both of these. We actually have two separate problems here, right? The one here on the left is a substitution one, right? If the derivative of tangent is secant squared, then I can use a u sub to give me a power rule integral. So here we'll get actually tangent squared x over 2. Right, and this one, which we did in class, is going to be the natural log of secant of x. Right, and again, you can also do this using a substitution. Right, the substitution should lead you to a 1 over x integral. All right, plus c. All right, now notice this last one here was a little different than the previous one, where we didn't get a nice a nice power rule integral across the board. So we're going to bring your attention here to this. So problem solving strategy, right? So when we have integrals that look like this, all right, so if j is even, you want to rewrite secant here, right? You want to keep a secant squared essentially to the side for your substitution. Okay, and then if k is odd, then you want to rewrite here in this manner. Right? You want to save a secant tangent x. Right? Okay, and then here they give different values for when k happens to be odd, k is even, j is even. Right? What you'll find out is here it'll really when it strays away from the first one, if k is odd, j is even, right? It requires, different. It won't be as straightforward, right? As we saw that it won't necessarily lead to a power rule integral, right? Sometimes we'll require to use different techniques, right? Maybe we need parts. Okay, so just keep that in mind. These are a little bit more not as straightforward as the sine functions.